Hello and welcome, all you statistical detectives out there. Today, we are cracking open a case that gets to the very heart of data analysis. And to solve it, we're going to be using a really powerful tool, the chi-square goodness of fit test. So let's jump right in and examine the mystery.
This is the fundamental question, right? You've got a theory, maybe a hunch, about how something works. So you go out and you collect your data, your evidence. But now comes the moment of truth. Does the evidence you found actually back up your story, or is something totally different going on?
So here's our game plan. First, we'll break down what goodness of fit even means. Then we'll get to know our main investigative tool, the chi-square test, and its rules. After that, we'll put it to work on 2 different case studies. And we'll wrap up with the key things you need to remember for your own investigations.
Okay, first things first. Before we can solve the case, we have to understand the lingo. So what exactly are we talking about when we say goodness of fit?
It's really all in the name. A goodness of fit test is basically a statistical showdown. It pits what you actually observed in your data against what you expected to find. It's the perfect tool when you're working with categorical data, things that fall into distinct buckets like colors or different types of products or survey responses. So, we've got our mystery. Now, let's open up our toolkit and look at our primary weapon, the chi-square test. And just like any precision tool, there are some rules you've got to follow to use it right. All right, don't let the symbols freak you out. This is the engine that drives our whole investigation. That little O just stands for your observed data, what you actually counted. The E is your expected data, what your theory predicted you'd count. So for each category, you just find the difference, square it, divide by the expected number, and then add them all up. The bigger the final number, the bigger the gap between reality and your theory. It's that simple. Now, before we go any further, we have to do a quick equipment check. There are 2 non-negotiable rules for the chi-square test. First, your data has to come from a random sample. No cherry picking. Second, the expected count for every single category has to be at least 5. This is super important for the math to be reliable. If you have a category with less than 5, you might need to combine it with another one. Always check these 2 things before you start. Okay, rules covered. Let's get our hands dirty and open up our first case file. We've got a car company, and they have a very specific theory about the colors their customers prefer. So, the company thinks they've got it all figured out. They have these exact percentages for what colors people will buy. To see if they're right, we've grabbed a random sample of 140 recent orders. Our job is to figure out if the real-world data from those 140 customers actually supports the company's claim. Every investigation needs 2 competing stories. First, there's the null hypothesis, or H0. This is the business as usual story. It says, yep, the car company's theory is spot on, and any little differences we see in our sample are just random chance. Then you have the alternative hypothesis. This is the plot twist story. It says, nope, something's off. At least one of those color percentages is wrong. Okay, time to crunch the numbers. First, we have to figure out our expected counts. How? It's pretty easy. We just take our total sample size, 140, and multiply it by the company's percentages. So for white, we expect 28% of 140, which is 39.2 cars. We do that for all the colors. Once we have our observed and expected numbers, we just plug them into that formula for each row, and then sum up that last column to get our final piece of evidence. And there it is. Our calculated chi-square statistic is 1.6315. This one number neatly summarizes the difference between what the company expected and what we actually saw. But the big question is 1.6315 a big enough number to be suspicious? So to make our call, we compare our statistic to something called a critical value. Think of it as a line in the sand. Based on our significance level and degrees of freedom, that line is at 7.815. Our number 1.6315 is way smaller than that. It doesn't even come close to crossing the line. This means we don't have enough evidence to call shenanigans on the company's theory. We fail to reject the null hypothesis, which is just the statistician's way of saying the data seems to fit the theory just fine. But hang on, let's take that same sample of 140 car orders, but this time, let's ask a totally different question. This brings us to our second case. Okay, so in this case, we're throwing the car company's theory out the window. We don't care about their specific percentages. All we want to know is, are all these colors basically tied in popularity, or is there a clear favorite? We're testing for a uniform distribution. So our competing stories have changed. Our new null hypothesis is super simple. All the colors are equally popular. Since there are 4 of them, that means each one should get 25% of the sales. The alternative hypothesis is that the playing field isn't level. At least one color is more or less popular than the others. The process is exactly the same, but look, our expected values are different now. If all colors are equal, we'd expect our 140 orders to be split perfectly 4 ways. So 140 divided by 4 gives us an expected count of 35 for every single color. Now we just run the chi-square calculation again with these new expected values.
Wow, okay. Our new chi-square statistic is 9.7714. Now that is a much bigger number than the 1.6 we got in the first case. So is it big enough to change the verdict?
And here's the big reveal. Our line in the sand, that critical value is still 7.815. But this time, our statistic of 9.7714 is clearly bigger. It crossed the line. So this time, we reject the null hypothesis. We have strong statistical evidence to say that no, the colors are not equally popular. It's a completely different conclusion, all from the same set of data, just by asking a different question. So, 2 cases, 2 very different outcomes. What's the big lesson here for you, the statistical detective, to take away from all this? Let's file this one away. Remember these 5 things. At its core, this test is all about observed versus expected. You can use it to check a really specific theory someone has, or you can use it to just see if things are distributed equally. The final call always comes down to comparing your test statistic to that critical value. And please, I can't say it enough, always check your assumptions, random sample, and expected counts of at least 5 before you even start. So now you've got this awesome tool in your detective kit. So think about it. Are people really born on different days of the week at the same rate? Do customers at a coffee shop really order different drink sizes equally? The world is just full of patterns waiting for a good detective to investigate them. So what are you going to investigate first?